Hello and welcome to my video presentation at this year's virtual ISPRS Congress. My name is Theresa Meyer. My today's talk is about accuracy investigation and image-based change detection for BIM-compliant indoor models. First of all, I will give you a brief introduction on the topic and our motivation for this contribution before I move on to the method overview of our change detection application. The main part is about the accuracy investigations methodology, including experiments and results. And finally, I will give you an insight in the next steps and a general conclusion. Change detection is currently of great interest for the construction industry and BIM. Camera pose estimation, co-registration, and thus image and point cloud interpretation are indoors much harder than outdoors. At the same time, meeting high accuracy requirements and dealing with metric confidences is essential in the field of civil engineering and BIM. In our approach, the initial BIM to be investigated itself serves as a geodetic reference and supports the interpretation of the obtained image data. Hence, this contribution gives an assessment on the geometric accuracy of image-based change detection in indoor environments based on a pre-available BIM. The overall concept is as follows. A stereo camera system with IMU will be used to easily obtain the relative orientation, the scale, and a relatively dense image-based 3D point cloud, which is further used to generate 3D line segments. Together with the results of the semantic segmentation of the 2D images, these 3D line segments can be extended with semantic information. In case of an abortion of the image sequence, the coarse absolute orientation can be determined from the matching of corresponding 3D line segments. But the main idea is to make use of any initial BIM information in order to support, improve, and optimize the change detection process. Known BIM objects which are identified in the images can be used to refine the camera pose and to achieve an optimal co-registration. Finally, the initial BIM is to be updated. And altogether, this results in a positive feedback loop, because the higher the quality of the initial BIM, the faster and more precisely it can be updated again. Line features usually serve well as geodetic references in indoor environments to solve for camera orientation and post-refinement. Model edges are projected and assigned to corresponding straight lines in the image. However, building edges are never perfectly built as planned, and they are often geometrically generalized for BIM-compliant representation. As a result, corresponding lines are considered as statistically uncertain entities with covariance matrices. Finally, the incidence condition is used for estimation in the projective space. The estimation is based on a Gauss-Helmert model with constraints. The corrected observations and the unknown parameters have to fulfill certain conditions. The G conditions describe the relation between the observations and the parameters. This is the incidence condition of a 3D model edge which is projected into the image with an observed corresponding straight line in the image. For the handling of singular covariance matrices, the homogeneous observation entities as well as the parameters must be spherically normalized. Therefore, we need the H restriction for the unknown projection matrix and the C constraints for the observations. The optimal solution is given by the minimum of the weighted squared residuals subject to the given constraints, and this is achieved by minimizing the Lagrange function. The inherent uncertainty of building models, especially those who are based on a so-called as-built documentation, have to be considered in the estimation. Therefore, the stochastic model includes the individual uncertainty information of BIM-related objects according to the level of accuracy specification for BIM. This document is provided by the US Institute of Building Documentation. It recommends standard deviations for professional building documentation. The homogeneous representations of model elements are extended with individual stochastic information using homogeneous covariance matrices. For each correspondence, the observation vector consists of a homogeneous image line and the endpoints of the corresponding model edge. The unknown parameters are the elements of the projection matrix. As the homogeneous entities relate to Euclidean BIM objects, their coordinates are expressed with respect to the BIM's reference system. And a big difference between the homogeneous and the Euclidean part causes the calculation to be numerical unstable, which is why conditioning is applied. Also, spherical normalization is necessary for the handling of singular covariance matrices. The corrections for the observations and parameters are calculated in an iterative manner. In every iteration, the Jacobians with the first derivatives of the various constraints are calculated. Please have a look at our paper to find a detailed description of the whole estimation procedure. The presented estimation model was tested for the optimization of an approximately known camera with synthetic data as ground truth for accuracy assessment. A virtual view of a detailed interior BIM was rendered, and this resulted in a synthetic image with a perfectly known camera pose and hence a true projection matrix. For the simulation of varying edge detection quality and of course different level of accuracy of the reference model, Gaussian noise of varying magnitude was added to the objects involved. The estimation finally starts with an artificially degraded projection matrix, as it might result from a stereo camera and visual odometry. P serves as initial value. It results from a standard deviation of 15 centimeters for translation and 1 degree for rotation. For LOA 10 to LOA 50, 100 simulations each were calculated with image lines of varying degrees of noise. Here you can see the results of LOA 10. LOA 10 objects have a standard deviation of 7.5 centimeters. The blue lines represent the projected model edges with the adjusted projection matrix after the estimation. Obviously, this is not a desirable result. The initial course orientation does not get better here. The reference model assigned to LOA 10 does not have a sufficient geometric quality. In contrast to the previous simulation with LOA 10, this one shows better results. The reference model is LOA 30 compliant, which means model edges have a standard deviation of only 7.5 millimeters. P gets optimized up to an uncertainty of 3 pixels for straight line detection. Following the recommendations of the US Institute of Building Documentation, it can be assumed that essential interior elements such as doors, walls, and windows are modeled at least LOA 30 compliant and are thus suitable as geometric references for co-registration. According to the specification document, LOA 50 models have standard deviations in the range of sub-millimeters. It is no surprise that these high accuracy references are perfect for co-registration. Here you can see the very good solutions that were achieved with LOA 50 simulation, but practically this demanding level of accuracy is very rarely achieved in real projects. Therefore, one should not assume that such models will actually be found in professional practice. We have shown that a coarse camera orientation can be improved to be accurate enough to reveal statements about relevant changes between the model and the actual state. BIM-compliant indoor models with usual geometric quality are generally sufficient and useful as geodetic reference for change detection applications. We will use the presented estimation model in further tests, including real data from different camera sensors. Also, the investigation of the effects of varying geometric conditions, such as the spatial distribution of line references, is planned. And also, we will further validate the reconstruction accuracy with optimized co-registration. In real-world use, it must be assumed that the reference model is faulty regardless of the LOA definition, and the as-planned state will likely not fully match the as-built state. Since outliers, mismatches, and deviations are to be detected in order to update the digital twin properly, a robust estimation has to be realized with an option for reweighting observations. That brings me to the end of my presentation. I recommend you to have a look at our paper to find many more information. Also, please feel free to contact me for requests by email. Thank you very much.